Welcome everyone to the next Gen 4 International webinar presentation. Today's presentation on scale effects and thermal hydraulics application to the French SFR will be presented by Mr. Benjamin Jourdy. Doing today's introduction is Dr. Patricia Pavier. Patricia is the group leader at the Pacific Northwest National Laboratory. She's also the co-chair of the Gen 4 International Forum Education and Training Working Group. Patricia, I give you the floor.
Thank you so much, Bertha. Good morning, everyone, and good evening. I'm very happy to have Mr. Benjamin Jourdy with us today. He graduated in 2019 from l'École Centrale de Marseille in the field of materials and structural mechanics. During his studies, he worked part-time for the French Atomic Energy and Alternative Energy Commission, the CEA, at Cadarache Center as an apprentice on the dynamic response of fuel assemblies in PWR and their seismic excitation. He designed the instrumental setup of a door, a mock-up with 3 fuel assemblies at scale 1-2, and performed experimental campaigns in representative conditions of PWR. Benjamin is currently completing his PhD in the field of thermal hydraulics on the subject scale effect analysis on the thermal hydraulic behavior of impinging jets in sodium fast reactor. His PhD focuses on the buoyancy effects of the core jets in SFR after impingement of the upper core structure and their transposition from small-scale mock-up to the reactor site. I would like also to note that Benjamin won second place of the 2021 Pitch Your Gen 4 Research Competition, which was organized last year by the GIF Education and Training Working Group. And you can watch his video at the link that you have here. So without any further delay, Benjamin, I give you the floor, and thank you again for presenting this webinar.
Thank you a lot, Patricia, and thank you a lot, Bertha, for organizing this event. So good morning or good evening, everyone, depending on where you are. So today we will talk about scale effects. First of all, I would like to say that the purpose of this webinar is to present an overview on the scale effect issues we can have in physics and in the nuclear field, and to present a methodology I'm currently applying to sodium fast reactor during my PhD. So first of all, maybe it could be interesting to define the scale effects. And it seems that I cannot change the slides, so okay, it is working. So first of all, I'm going to provide a quick definition of what is a scale effect. It can be seen as a distortion of a physical phenomena between a downscale mockup and a full-scale prototype. Scale effects, they usually come from a variation of the length L, because when you change the length of a system, you change the area because they are multiplied by the square of the length, and you change the volumes because they are multiplied by the cubic of the length. So an example we can have of scale effect in nature could be with the example of a mouse and an elephant. Let's take this example. We have a mouse that will be a size L. So the area of the mouse will be the cubic of the size L, and the volume will be, the area will be the square of the length L, and the volume will be the cubic of the length. Now let's say that we have an elephant that is 100 times the size of the mouse. So it is 100 L. The area will be 10,000 times this length L, and the volume will be 1,000,000 times this length. It will lead to a surface to volume ratio that is 100 times lower for the elephant. And we know that the surface to volume ratio is important when you are losing your energy with your environment, when you have to keep your body at the same temperature. It leads to a funny scale effects, saying that the mouse has to eat 100 times more than the elephant, when of course we are relative to weight, just in order to maintain the body temperature. This is something we can verify in the nature. Usually the mouse has to eat the equivalent of its own mass every day, while the elephant only has to eat around 5% of its own mass every day. This is an example of just a scale effects we can have in nature, but today I'm not here to talk about mouse and elephants. We will talk about hydraulic. So scale effects example we can find in fluid mechanics. I'm just showing 2 different kinds of scale effects. On the left, you can see a waterfall that is scale 1 to 30. So on the left part of the left figure, you can see the downscale mockup, and on the right, you can see the full size prototype. you can see that we have really different properties of the flow, because even if we keep the same discharge between the mockup and the full-scale prototype, we can see that we have air entrainment that is really different between them. It comes from a deviation of a dimensionless number known as the Weber number. But this is an example we can see with our own eyes that, okay, we should be similar. We just replicate it at lower scale, but we can see it is completely different. In a more mathematical approach, something we can see is about gas entrainment criterion. The gas entrainment is something you can have in your bath tube, for example. This is something we can find also in sodium fast reactor. And this example of scale effects come from a study from Eguchi and al., explaining that, okay, they were looking for a criterion of the moment we can start to have this gas entrainment. And it seems that the criterion used, being the fluid number, is changing with the scale ratio, as we can see here. So it is an example, more mathematical, of scale effects we can find that, okay, we have different critical values depending on your scale. So in fluid mechanics, this is more scale effects we can find. But today we will talk about nuclear. In nuclear field, because in fluid mechanics, when I was showing you, for example, the waterfall, it is something pretty easy to study. But in nuclear power plants, because today we will talk about thermohydraulics in nuclear reactors. In nuclear power plants, we have a really complex flow, most of them being transient, and because it is fluid mechanics and thermohydraulics, we have a lot of difficulties to establish closure laws. So the problem is that it is quite difficult and expensive to build a scale 1 reactor only to perform some tests. So a really powerful tool we have in the nuclear field is the use of the numerical tool for scaling validation when we are trying to create new prototype or new design for experimental reactors. So we are using the numerical tools, but the numerical tools, the code, need a validation, and we are validating them with small scale experiments, which leads to the question, how can we ensure the validity of a small scale experiment to a reactor size, and how can we transpose these results? So here on the right, I'm just showing you a quick methodology usually used to validate some code using some separate effect tests for a better phenomenon understanding, where we develop some model that we try to improve. We validate with some experiments at not exactly small scale. We separate effect test and integral effect test in order to find the better code possible, but we still have to evaluate some uncertainties and some transposition coefficients between the small scale mockup and the full scale prototype. So could we please, because it's still not working for me, move to the next slide, please, Berta? Thank you very much. So today we will talk more especially with the French sodium fast reactor problem we can have and why do we need to perform some experimental study to determine the scale effects. So first of all, let me talk a bit to you about the ASTRID project. So ASTRID stands for Advanced Sodium Technological Reactor for Industrial Demonstration. It was a project launched in 2010, where the aim was to build French sodium fast reactor in CEA in Marcoule. Unfortunately, this project, the project to build the physical reactor, stopped in 2019. Instead, the CEA is working on a numerical reactor in order to simulate the whole behavior of the whole reactor. So the problem is we are using code, so we will need some validations, of course. Just to clarify, today we will talk. Oh, it seems that the images moved a bit. We will work especially on the hot plenum thermohydraulic. So today's presentation will only focus on, if you take a look on the right, on what is in red. In the red part, which means it is all the upper plenum, where we can find the upper core structure and the intermediate heat exchangers. This is the part of the reactor we will talk about today. And in this zone, I can already show you some simulations that were performed by Areva in 2013. So it is, of course, numerical simulation of the velocity profiles, as you can see on the left, and on the temperature profile you can see on the right. This simulation, so we can at least have a first idea of the flow inside this zone. And of course, as I keep saying, we still need to validate code with experiments. So what we are doing, we have a mockup in CEA Cadarache named MICAS. It is a scale 1, it is a downscale 1 to 6 of the hot plenum of the asteroid reactor, and it is an homothetic transformation, which can be seen as a linear scaling. Everything is reduced of a factor 6 on the side. So of course, all the area are reduced by a factor 36 and the volume by a factor 216. This mockup represents, as I show, the main component we can find in the hot plenum of a sodium fast reactor. So we can find the core where, of course, we do not have a fissile reaction here. We only can put some water to replicate the thermohydraulic behavior. We can find the upper core structure and the heat exchangers in the diverse zone. Also to note that we are using water to perform our experiments instead of the sodium because it is easier to perform measurements in water instead of sodium because of its opacity. So now we will talk a bit about the kind of flow behavior we can find in a sodium fast reactor. This is the numerical modelization in the MICAS mockup, but that is representative of what is happening inside French sodium fast reactor in the asteroid reactor. First of all, we start outside of the core. In this zone, we have 288 hot jets. When I said hot jet, it is 575 degrees in asteroid, and it is around 60 degrees in MICAS. Then these 288 hot jets are going through a porous plate and impinging the upper core structure. Then in this zone, all the jets will merge and diffuse into the vessel as one radial jet. And inside the vessel, we will have a colder environment that will be around 550 degrees in asteroid and around 57 degrees in MICAS. So why is the environment a bit colder? It is because close to the core, in another part of the core to be exact, we have some cold jets. When I say cold jet, I'm talking about 400 degrees in the asteroid reactor and 10 degrees in MICAS. It doesn't have a low, it has a low mass flow rate. As we can see here, it is in this zone that we're injecting some cold jets. So it leads to a mixing temperature that is a bit lower than the hot jets want, even if it is close, because we have more mass flow rate going through the hot part than the cold one. So now that we understand that, okay, we will have a lot of jets impinging a structure and diffusing into the vessel when the temperature is a bit lower, we can start to talk about the issue we have in this phenomenon. The main issue I will talk to you today is that at low power operating conditions, we start to see a rise of the radial jets. So when I talk about the radial jets in this presentation, it will refer to this zone, the jets that come from the merging of the 288 jets after impingement. In this zone, so here I'm showing you some PIV experimental results on the MICAS mockup. At nominal operating condition, we should have a jet going downward, as we can see here. But what appears at low power operating condition is that we can see that the jet is not going downward as it should, and is even going upward. That can lead to some issues inside the reactor. The main issue we can talk today is about the consequences that the flow pattern inside the vessel will be modified. It will lead first to thermal oscillations, leading themselves to thermal stress of the components. So of course, if you have some components that are getting hot and cold, it will lead to some stress on the materials, and it will reduce the life expectancy of the whole plenum of the reactor. Now, the problem we are trying to solve today is under which condition does the jet rise? And then when we will start to understand the phenomenon, the physical phenomenon, how can we transpose these results from the MICAS mockup to the asteroid reactor? So it leads to the point that we are discussing today, that we need a scale effects analysis, and we choose to do it with an experimental approach in order to determine the scale effects and the transposition of this phenomenon. So now we'll talk a bit about the method we can have when we have to deal with scale effects and what is currently used in the literature. So first of all, we have to talk about what is a similarity. So when we have a downscale mockup, that is scale 1 to lambda, lambda being the scale factor. In the case of MICAS, lambda is equal to 6. We can achieve something that is completely similar to the real world prototype. So in our case, to the asteroid reactor, if we satisfy 3 criteria according to Heller. First of all, we have to ensure that we have a geometric similarity, which means our mockup has to be perfectly similar in shape. We should not perform some geometrical distortion. And it leads to the consequence as I show you with the mouse and the elephant, the length, area, and volume has to evolve with the scale factor being itself, the square of itself, or the cubic of itself, respectively. Then, once you have the geometric similarity, you have to ensure that you get a kinematic similarity, which means a similarity of motion. It means that you have to get a constant ratio of time, velocity, and acceleration in your mockup in order to be representative of the reality. And then once you can ensure the geometric and kinematic similarity, you have to ensure that you get the same dynamic similarity. The dynamic similarity is saying that we have to get identical force ratio at each point of your mockup. Unfortunately, for the people that have already been doing some fluid mechanics, we know that not all force ratio can be preserved. Most of the time, we have to select the most dominant one because each phenomenon usually have a dominant force ratio applying on it. And then we have to consider the other one as negligible. But sometimes we have too many force ratio that we have to take in account, and we have some of them that are not negligible. So of course, when you try to neglect some force ratio that should not be, it leads to scale effects. So the whole problem comes from the similarity between a mockup and full-scale prototype. So we get some different scaling techniques. First of all, of course, the main point is to target the phenomena at both local and system level. So when I talk about local level, it is exactly what I'm doing with my jet. We have to, first of all, we could perform a dimensional analysis. It is an empirical approach, which means we will try to find some correlation and models to derive similarity parameters, which means we would perform some experiments and say, okay, it will work this way, and we can transpose this result from a scale to another and try at least to estimate some distortions. Unfortunately, this empirical approach is not, you cannot always have a strong confidence in this kind of approach. So when you know how your system is behaving, you can use the dimensionless governing equation, which is a more mechanistic approach. The dimensionless governing equation in fluid mechanics being known as the mass, momentum, and energy conservation. So usually you have to simplify the governing equation with your assumption on your flow, and you can compare by putting it in dimensionless form. You can compare the non-dimensional terms between the model and the prototype in order to estimate what force ratio are you keeping and which one are getting are getting some distortion, and evaluate the effect of the distortion. This is for the local system level. Then you have to work at for the local level. Then it is the system level that you have to deal with. Because from this approach, you can find some scaling laws from different governing equation with some dimensionless parameters you have to keep from a scale to another. And you can then try to identify all the phenomena happening and rank them in a PIRT, being a process identification and ranking table. So this is how we deal usually in the nuclear field with scaling techniques in order to avoid scale effects. So now I talk a bit about the Vashi-Buckingham theorem. So the first point I was talking to you about targeting the phenomena at local level. It is the empirical approach. The Vashi-Buckingham theorem is a simple and direct manner for the formulation of criteria for dynamic similarity. So let's say you have a physical problem. You will have n independent parameters. These parameters can be the velocity of your flow, it can be the density, it can be the temperature, it can be a lot of parameters, and you will have R reference dimensions. Your dimensions being the time, the temperature, the mass, the length. The Vashi-Buckingham theorem is just saying that you will find n minus R independent dimensionless parameters. It can be geometrical parameters, it can be force ratio. You will find some geometrical parameters, even if your system is behaving like a black box, you don't really know what is the physics happening, you will still be able to find some geometrical and force ratio parameters. Unfortunately, with this theorem, the relative importance of the dimensionless number remains unknown. It leads to an arbitrariness in determining the similitude condition, because if you have a lot of dimensionless parameters, you are not able to say, okay, this one is more important than another one. So this is why the Vashi-Buckingham theorem, this kind of empirical approach, is strongly criticized when you have more than 6 dimensionless parameters that you have to keep between a scale and a mockup, between a downscale mockup and a prototype. So usually what we are doing is try to understand and find the governing equation of your system. As I said, in fluid mechanics, the most governing equation, the most common used equation are the mass, momentum, and energy conservation. Using this dimensionless equation give you information about the relative importance of all terms you can find from a scale to another, and you can compare this force ratio. For example, if I take here the Navier-Stokes equation, if I decide to keep, for example, the Reynolds number, I can see the distortion it will lead to the Euler number, to the Froude number, etc. One small hint about this techniques is that the geometrical parameters are not taken in account. If you perform the geometrical similarity, it is not a problem. If you have to create some distortion, you will have no information about some ratio you should keep from a scale to another. But most of the time, the dimensional analysis is way more powerful than the Vashi-Buckingham theorem when the equations are known. So now let's talk about some scaling technique example we can find in the literature and we can find in other countries, for example. First of all, the first scaling techniques, the most common use, of course, is the linear scaling. It is exactly what we are using with MICAS. It is just saying we keep exactly the same aspect ratio and velocity. So we just do the exact replica of a downscale mockup. Unfortunately, while doing it, we cannot have a downscale universe around our mockup. We have some constant, universe constant, let's say, that will remain. For example, by doing a linear scaling, the gravity stays the same on a smaller mockup, which leads it can excessively distort the gravity effects. We can have an overestimation of some gravity effects by doing just a linear scaling. When we have some issues that are dealing with gravity effects, we can use other techniques. Just presenting one today that is known as the power to volume scaling. And I'm showing you on the right an example. It is PKL, PKL standing for the German word for primary circuits of a PWR, a power pressurized water reactor, sorry. And this is a mock-up you can find in Germany at Framatome in Erlangen. So the power to volume scaling techniques is a powerful technique to keep time and heat flux. Because it is a scale 1 on the height, it has a geometrical distortion. The height is a scale 1, but the volume, for example, are scale 1 to 145. You will have no distortion on the gravity effect thanks to the same height. But we will have other distortion because you reduce the volume. It leads to excessive heat stored in the structure instead of in the flow, and higher heat loss because you have a higher surface to volume ratio, as we can have, for example, with a mouse. So we will lose more energy. So it is distortion you are creating, but it is perfect scaling techniques when you want to study some accidents. For example, some natural circulation will have during loss of coolant accident or other studies they can make in this facility. So it is a distortion you can have when you have one specific issue and you don't really care about creating new distortion because you have no distortion on your target phenomena. You have other techniques that are way more mathematical. So for this slide and the next one, I will be a bit quick because it is not exactly the point of the presentation of today. I'm just showing you for the people that may be interested in this. For example, the hierarchical two-tiered scaling technique. It is a technique that's, okay, you have to perform a system decomposition when you have a really complex system. You divide it into subsystems, each subsystem being divided themselves into module, constituent, phases, etc. So you have to perform some scale identification. You will define some volume fractions, spatial scale, and temporal scale. And then, first of all, you do a top-down analysis. So you do a scaling hierarchy in each component, each module, etc., using the governing conservation equation. Then you can perform a bottom-up analysis in order to get some scaling criteria and define the time constants you will get in each of your, let's say, of your box. It is a method. I'm not talking too much about it. I will provide you some references at the end of the presentation if you're interested in that kind of method. It is usually used and compared with other kind of methods, such as the fractional scaling analysis. The fractional scaling analysis is an analytical approach for complex problems, such as you can find in fluid mechanics, of course, but also in economy or in ecology. It is a strong techniques when you have some variables that are getting influenced by convection problem, diffusion problem, or wave propagation. When you have other issue with, for example, some scaling distortion because of time dependency, you have a recent innovative approach known as the dynamical system scaling. I'm not talking too much about this method because I don't know it well enough to present you today, but I will provide you some references that may interest you if you have some scale effects and with time dependency, let's say time dependency phenomenon. Because today I will talk to you about the experimental approach for scale effect determination in the French sodium fast reactor. So what is the purpose of my work during my PhD on the MICAS mockup? First of all, I will present you the general methodology when you plan to perform some experiments in order to understand the scale effects you will have. So first of all, you have to perform a dimensional analysis. So this is what I already presented you. You are using either the Vacher-Buckingham theorem when you don't exactly know how does your system behave, or you can use the dimensionless equation to find the similarity parameters. It is to get a general understanding on your phenomenon. Then what should be done is when you have to perform a calibration, which means you need some scale 1 prototype data, and you need to compare results on small scale mockup with the scale 1 prototype data. If there is a deviation between your small scale mockup and your prototype, you can perform some correction or at least get an estimation of the scale effects you will have. In our case, it's going to be a bit more difficult because no astute data are available. That is the whole problem. We are not building the physical reactor. So when you cannot have access to prototype data, what we can do is we are performing a method named the scale series. It leads to the fact that the scale series is explaining that we need 3 similar models at different scale. When you cannot have prototype data, you use your biggest scale as a reference scale. And the deviation you can see between the downscale mockup and your reference scale will provide you information and your quantification of the scale effects you will have. In our case, because during my PhD, we cannot build a bigger scale than MICAS that is already scale 1 to 6 of the astute reactor, we will use this as a reference scale saying, okay, it is a bigger scale we will have. So now what I had to do is to design 2 new mockup to be representative of the MICAS flow and what will happen in sodium fast reactor. So now that we know we are going to perform the scale series techniques, let's apply the Vacher-Buckingham theorem. Okay, here it is a schematic of what is happening. We have hot jets coming out of the core, going through the porous plates, and okay, at nominal flow rate, just a reminder, the jet is supposed to go downward, but when we have a low mass flow rate, the jet will go upward, as we can see here. So first of all, we list all the governing parameters. It can be either geometrical parameters, such as the height, for example, between the porous plate and the exit of the core. It can be some temperature, it can be density, and it will lead to a group of dimensionless numbers. So here, using the Vacher-Buckingham theorem, you can see that we have 9 dimensionless numbers. Some of them are geometrical, such as P1 or P9. Some of them are force ratios, such as P2, P3, or P4. Some of them are just about the temperature differences or properties of the flow. You can also have some thermal dimensionless number, of course. As I said, when you have more than 6 dimensionless parameters, this approach is strongly criticized, and we cannot, just looking at this array, say, okay, this dimensionless number can be neglected and this one cannot. So we will also use, of course, the governing equation. So using the dimensionless Navier-Stokes equation with some assumption we can find in while studying turbulent jets. So because the Vacher-Buckingham theorem is not really suitable for this, we are putting some assumption into our dimensionless Navier-Stokes equation. We are assuming a stationary flow, and we are assuming that the Boussinesq approximation is valid in our case. So it leads to the fact, using the theory of turbulent jets, that we have 3 to be exact dimensionless number that are coming. We have the viscosity term known as the Reynolds number, and we have the buoyancy term being a mix of the Froude number and the densimetric Froude number. So this is what we can get using the dimensionless equation. And we can find it back. For example, the densimetric Froude number is just P4 multiplied by P8. It is something we could have seen with the Vacher-Buckingham theorem, but that was not explicitly written in it. So this is why it was important for us to use the governing equation too. And in our case, we are making an assumption at first, saying that the rise of the jet is owing to buoyancy effects. So if we follow this assumption, it will lead to the fact that the densisymmetric Froude number may have a strong influence and should be used as a scaling parameters, at least to see if this ID can provide good results about scale effects or not. So now our assumption will be that the densisymmetric Froude number will be used as the scaling parameter to go from a scale to another. So as I said, we have to design two new mockup now that we understand a bit more the theory we have behind these jets. So first of all, when you want to study some scale effects, it is important for you to know that you should be able to get some scale factors as far away from possible from them. If we had, for example, MICAS that is scale 1 to 6, and we're creating another mockup that is scale 1 to 6.5, we will not create enough distortion to be able to see if we have scale effects or not. So first of all, we try to define our maximum scale. The maximum scale in our case is because of material limitation. We are working on a loop that will have a maximum mass flow rate of 15 cube meter per hour. And it creates, by applying the similarity of the densisymmetric Froude number, it will lead to a maximum facility size of 1, 2.5. The problem, because of course we want to ensure the similarity of the flow, by doing it, it will lead to 288 laminar jets. The problem is, if we are doing this, we are creating a scale effect. We are creating a distortion of the physical properties of our flow. So we had to find a solution, and the solution is to create a geometrical distortion in order to avoid a physical distortion. So we reduced the jet number. Instead of 288 hot jets, we decided to get only 19 bigger jets. By increasing the jet diameter, we will ensure the turbulence of the flow. And of course, in order to not create too much distortion, we studied the merge of the jets to make sure that we will find an equivalent flow by having less but bigger jets in our setup. So we performed this study in order to make sure that we will not create too much scale effects and avoid, let's say, a distortion on the turbulence of the flow. So here we can find, let's take a look at the picture on the right at first. In this zone, the fissile zone, you will have all the hot jets. And you can see in green, for example, the cold jets I was talking to you at the beginning of the presentation. On the right, on the left here, I'm sorry, you will find the core in the MICAS mockup with the 288 hot jets in the middle and the cold jets on the periphery in this zone and in the peripheral zone. What we did, as I said, we increased the jet diameter. We keep the same aspect ratio, but we increase each jet diameter. We reduce the number in order to keep the turbulence of the flow. The cold jets were already laminar on the flow in MICAS, so we choose to keep them as close as possible from the reality using the scale ratio while downscaling the phenomena. So now that we have this criterion for the higher scale, we can also use the same to find the minimum scale we can have, because we still have to be able to ensure the turbulence of the flow on the whole range of the study. So for this, it leads to a minimum scale of the mockup I designed of 1 to 4 of MICAS. But other distortion can be performed, sometimes not in order to avoid some effects, but in order to study them. Let's take a look at what is known as the upper core structure. The upper core structure is the part just above the core. It is used for some instrumental setup in sodium fast reactor. You can see these tubes. They are known as schist tube. The jets going out of the core here, some part of the flow will go inside, and they will go inside the upper core structure, flowing through these holes you can see in this zone. Of course, it is leading to loss of pressure coefficients, and we already know that it is non-linear with the velocity. So what we decided to do with a small scale mockup is that we choose to reproduce the zone under the upper core structure in order to keep the same flow repartition in this zone and to not provide a perturbation after the impingement of the flow repartition. But we choose to replace the part inside the upper core structure with an adjustable piston in order to be able to modulate and change the loss of pressure coefficient inside the upper core structure. Here, the main point is we want to create a distortion in order to see the effect of this distortion on our phenomena, to make sure that, okay, does this have an influence or not? And to define a validity domain for which we can say, okay, our phenomena, the rise of a radial jet, is not influenced by the loss of pressure coefficient we can find under the upper core structure, or maybe it is. This is something that we will see later. So now I can tell you that the small cap mockup, known as Morito, it will be scale 1 to 4 and 1 to 2.5. And as I said, we are using MICAS as a reference scale, just here. So this is the whole range of the study we will be able to perform to see if we have distortion. For example, we will be able to compare results from scale 1 to 4 to scale 1 to 2.5, and results from scale 1 to 2.5 to scale 1, and of course from scale 1 to 4 to scale 1, in order to see, do we have scale effects? Is there any distortion? And if so, we can see either the distortion and the evolution of the distortion with the scale, in order to find some, at least on first approach, some transposition parameter in order to go from scale 1 MICAS to the scale 6, because it will be, of course, Astrid will be the scale 6. So I'm here providing, sorry, I'm here showing you some pictures about the Morito setup scale 1 to 4. You can see the replication of the upper core structure. You can see here the porous plate. Everything is identical as we can find in MICAS, except of course for the distortion of the hot jets, as I was saying. And you can see my hand for scale, just to show you that it is a really small mockup that is supposed to represent a whole nuclear reactor. So now, because as I said, we will have to compare results from a scale to another. So maybe we should start to have some results, and we will start with the scale 1 result we will have on the MICAS mockup. First of all, I am sorry, I will still have to talk a bit about theory, but this time not theory about scale effect, but theory about the rise and the drop of a jet. The rise of a jet can be defined with 3 parameters. First of all, you will have the half width L0 of a jet, saying that, okay, if you had, for example, a round jet, it will be equivalent to the radius. So you will have the half width of the jet. You will have the distance from the exit of the jet to its rise or its drop, depending on what you're studying, this distance, xz, and you will have a final angle, theta f. Usually, the xz relation is known. It is something that have been studied a lot in bibliography. I'm showing you here a reference from Papakonstatis and all. It is saying that, okay, we already know the theoretical relation between this distance and the densimetric front number, and of course it is related to the half width of the jet. It is saying that, okay, this ratio is equal to a constant that only depends on the initial angle. So during our study, because this is already known, we choose to focus on the evolution of the final angle to see, do we have scale effects on this final angle. For the rest of the presentation, we will adopt a convention about the jet angle, the jet final angle. At nominal mass flow rate, as I said, we have a jet that will go downward. If we have a jet that goes downward, because it is a nominal condition, we adopt a convention saying that this jet has an angle above 0. So the angle will be positive. When the jet is going upward, the angle will be negative. For example, here we have something that is around minus 30 degrees. So now that we have this convention, we can talk about experimental setup. In order to find some at least velocity results, we will use a method that is known as PIV. PIV stands for particle image velocimetry. We are using nylon particle that will be around 4 micrometers and a 4 megapixel CCD camera. For the people who may not know what is PIV, it is a method when you put some nylon particle, or it can be other particle, but in my case it is nylon particle inside your fluid. And this particle, because their density are really close to the fluid one, they will move with the flow. So then what we are doing, we are using a laser that will provide a laser sheet that will unlight these particles. Then perpendicular to this laser sheet, we have a camera. The camera will record, we picture 2 frames very close to each other. And so we will see between the two frames the particle moving. And because we know the time lapse between the two frames, we can define how does the particle move. We can go back to, we can find the velocity of the flow. So it is a method to find the velocity of the flow. It is instantaneous results. In my case, I am working on a stationary phenomena. So we are averaging 150 images, which is a bit more than 10 seconds of acquisition, using a software named Insight 4G in order to perform the PIV measurements. Why are we doing PIV measurements? It will help us find experimental results on the final angle, θf, which is the main point that is interesting me to study the scale effects on it. It will also provide me information about the jet half width, L0, and I will find the radial jet velocity. But we also need to perform to get some temperature measurements. So the temperature measurement, we are using PT100 probes because they have a really low uncertainty. We are using them to get the hot jet temperature, to get the environment temperature that we can get in the environment and also in the pump pit where everything is getting mixed. And we can find it in the upper core structure to make sure that we are not losing too much energy between the outside of the core and this zone. And we are also using some thermocouple just to get information about the stratification and to make sure that during our experiments, we have a stabilized flow. So what is the output? Of course, we are expecting from this measurement, it is to get, as I said, the jet temperature and the environment temperature in order to find the density differences we can have between hot jet and a colder environment. And now we have to talk a bit about the experimental condition we will apply. So first of all, we keep an identical flow repartition in the core as we had as we should have in the asteroid reactor, which means 95% of the mass flow rate will be in the hot jets and only 5% of the mass flow rate will be in the cold jets. And because we have to define our similarity criterion, we choose to keep the densitometric flow number, as I said before, we find with the dimensionless governing equation. We choose to keep it at the core exit. And keeping the same densitometric flow number at the core exit should provide us, let's say, experimental conditions that are supposed to be close to the one we will have in asteroid while studying the thermohydraulic on this special issue. But we have to change the densitometric flow number in order to see the dependency on our phenomenon, which is, as a reminder, the rise of a jet. We have to study the dependency on the rise of the jet with this dimensionless number. So what we will do is that we will change the densitometric flow number out at the core exit to see how does our system behave while the densitometric flow number is changing. So we will have experimental, let's say experimental condition going from 20% to 100% of the nominal flow rate in asteroid using the similarity of the densitometric flow number. And we will change the densitometric flow number by changing the mass flow rates, because we have two ways to change it. Either we change the density differences with the jet and its environment, or we change the velocity. It is way easier when you are doing experiments to only change the velocity and keep the same temperature. And now let's see some results. First of all, I am just showing you 4 PIV results. It is the images. What you are currently seeing are the velocity vectors in this zone. You have just here the upper core structure. We are still looking at the jets outside of the core after impingement when the 288 hot jet already merged. So what we can see, it seems that, okay, at least with our experimental range, we could capture the moments before when the jet is going downward as it should, and we can see it start to rise. Picture 3 and picture 4, we can see it getting really high. So at least our experimental condition could ensure that we can study our phenomenon. Then what we seem to see from picture 1 to 3 is that when we decrease the mass flow rates, we are seeing a jet going more and more upward. But we have an issue between picture 3 and 4. We can see that the jet is going more upward, has a higher or lower angle depending on the convention. For us, it is, let's say, a lower angle, it will be more negative. Even if we have a higher mass flow rate compared to the one we have on picture 3. But we also can notice that on picture 3, we have 2.1 degree differences between the jet and the environment. In the picture 4, we have 4.4 degrees differences. It leads, when you are comparing the densitometric front number, to the fact that while decreasing the densitometric front number, it seems that the jet is going more and more upward. And it is something that we can definitely see on the 4 pictures. We start at the densitometric front number of 41 with the jet going downward, and we're just, the more you decrease it, the more the final angle is getting important, or less important depending on the convention. Of course, it is still negative in our case. So let's study it a bit more. When you get some PIV results, you have to, at first, you just have an image. You have some vectors. You have to find yourself how you can calculate your conditions. So I'm just showing you how I am doing it. First of all, I developed a Python code to define a window in this zone. And you are using the theory of turbulent jets, saying that the maximum velocity you can find in the jet is in the center of the jet. So by plotting only the maximum velocity on the final angle of the jet, you can find kind of the jet angle by just doing a linear regression in this zone. So it is helping us to get an approximation of the final angle. What we also need is we define another window because we still need the half width of the jet. So in this window, we decided to plot all the velocity vectors. As you can find here, we can find kind of the same profile as we should find in theory, saying that a hot turbulent jet has a Gaussian profile. And we define a criterion saying that, okay, we say that a velocity vector belongs to the jet only if it is above 10% of the maximum velocity, because else we get some vectors, for example, that are not really in the jet because the flow is still moving a bit around. Then once we get it, we have the radial velocity, we have the half width, we have the angle. We can define a radial jet densitometric front number, which is the equivalent of saying, okay, let's say we did not really had 288 hot jets. What would have happened about the physics if it was just one radial jet? We have one jet diffusing into a colder environment. This jet would have had an initial densitometric front number that we can calculate this way using the experimental velocity in this zone that is calculated, as you can see here. And you can keep, of course, the difference of density between the jet and the environment. And you can use then the half width of the jet L0 that we experimentally found. Once we define this radial jet velocity, you can keep going with the study. It is what is plotting here in blue. So in blue, it is the evolution of the angle of the jet, the final angle of the jet, with the densitometric fluid number calculated after impingement, as I showed just before. In this zone, what we can see is that it seems that we have a linear evolution of the angle with the densitometric front number. What will be interesting for us for the rest of the study is to use the critical densitometric front number that we define as the value of the densitometric front number for which our jet is going from a downward jet to an upward jet, which means it is the value for which theta f is equal to 0. It is important for us to know it, to compare it from a scale to another. And then this is what we have, for example, if we were just using one radial jet. In our system, the physics is a bit more complex. We have 288 hot jets. So what we are doing, and what we did, in fact, is that we applied the similarity of the densitometric front number not in this zone here, but we applied it at the core exits. So we are doing the same as previously. We are plotting the evolution of the final angle with the initial densitometric front number, initial being meaning that it is calculating at the outside of the core. It seems that we have the same kind of evolution. We still have one linear zone of the evolution of the final angle with the densitometric front number, and then we have an asymptotic zone that we have on both ways. It is the angle we get when we have a high densitometric front number, which means a really high inertia, low buoyancy effects. So it is the angle you can see here when the jet is going downward. It is an angle around 20 degrees. First of all, maybe some of you may have noticed between the plotting in orange and the plotting in blue, it seems that we have a similar behavior. it is not something that was obvious because while calculating the jet outside of the core, they are going through nonlinear phenomenon. A part of the mass is going through the schist tube and going inside the upper core structure. We have loss of pressure because of the porous plate, and we are losing energy because of the impingement. It was not something obvious that we could find the exact same behavior. What is really changing is the value of the densitometric fluid number we have in these two zones. So we tried to study the effects, for example, of what is happening if we wanted to find a relation between what is happening outside of the core and what is happening in this zone. For this, we choose to normalize our results. So the normalization is made by the nominal densitometric fluid number that we should have at nominal condition, saying that, okay, when you have a densitometric fluid number normalized equal to 1, it means it is what should happen when you have 100% of your nominal mass flow rate in your mockup using the densitometric fluid number similarity. You have the definition just here. What is happening is that we can see the two curves are really close to be the same. It leads to a first preliminary conclusion that maybe we have no real influence of the nonlinear phenomenon under the upper core structure, so about the schist tube and the porous plate. It seems that all the nonlinear phenomena happening in this zone may be negligible, completely negligible, when you are studying the effects of the rise of the jet. It leads to another conclusion that maybe after normalization, we could say that 288 impinging jets can be studied as one free radial jet. And why is it really interesting for us? Is that because you don't have a lot of bibliography about the thermohydraulic behavior of 288 hot impinging jet in the literature. But one free radial jet in a colder environment, you have a lot of documentation about it. So we still have to find the exact transformation from the core exit to the radial jet. But it seems that with a normalization, we can get really close results and maybe simplify our study. So the next step, because of course this is all we have with the MICAS results, but we need other results to compare from a scale to another when you are performing some scale effects. First of all, we are using another mockup named Piña to get a better understanding on exactly what I said, which means how can we how can I say it? How can we understand what is happening after impingement and find a relation between the densitometric fluid number after impingement and the densitometric fluid number at the core exit? So the Piña setup is an oversimplification of the MICAS mockup and the Morita mockup. It is just one single jet. Yeah, you can see the single slot jet here impinging a flat plate. We have no geometrical representativity. We have no really scale representativity. It is more an oversimplification in order to study the question we are trying to answer is, will the jet angle get the same evolution and the same critical value as we get in MICAS while we are just studying one impinging jet? So the phenomenology we are studying is the evolution, of course, of the angle with the densitometric fluid number. We are also trying to evaluate some distortion we could have by changing, for example, the h divided by d ratio, because we can change the distance you can have between the jet and the impinged plate. Our main point is still to find a theoretical and experimental relation between the jet exit and the radial jet in order to try to apply this to MICAS then to say, okay, if we are studying one free radial jet, we can say that in our reactor it will behave like this because we know how to transpose results from this zone to this zone. So this is just now let me show you some experimental results we already get on the Piña setup. So there's preliminary results. PIV results, you can see that, okay, from the left to the right, we are decreasing the mass flow rate. You can see that, okay, increasing, sorry, the mass flow rate. So you can see that the more you increase, of course, the mass flow rate, the less the buoyancy effects will be important. So the more your jet will go downward. First of all, we can already see that when you really have a lot of inertia, for really high densitometric fluid number. I cannot show you exactly the value yet because we are still calculating some. These are some experiments that we performed 2 weeks ago. I still don't have time to analyze everything, but we can already tell you that we have one geometrical influence, because when you have a high densimetric Froude number, in the MICAS mockup, we could see that the jet was going downward. On the PINIA setup, you can definitely see that the jet is not going upward, it is staying at a 0 degree level. It already provides us some information about a geometrical influence you can have, because on MICAS, maybe this is something I did not really show, but you have some part here that may have an influence on the flow. With this mockup, we already show that it has an influence on the flow. So maybe with the Morito mockup, we could show that decreasing this distance too may be important for the jet angle. So now what is happening with the Morito mockup? The experimental campaign incoming, I am sorry, I cannot show you right now results to compare with the upper scale MICAS. The experimental campaign is coming, and what will be compared with the MICAS result are the critical densimetric Froude number. So just to remind you, it is the densimetric Froude number for which we will have a final angle equal to 0 degree. We will also compare, so it is this zone, sorry. We will also compare the slope of the evolution of the angle. This slope we can have from a scale to another to see if the system is really behaving the same. And we will try to find also, do we have a constant angle for high densimetric Froude number? For example, on the MICAS mockup, we have an angle of 120 degrees. Maybe on Morito, we could have something that it will be 10 degrees or maybe 30 degrees. We don't know yet. And if we have differences, it will be directly scale effects. So as a conclusion, first of all, the question is, how can we conclude? So as I said, it is still an ongoing study. I am really sorry I cannot provide you all the conclusion right now. We still have to wait a little bit. If we have no scale effects, what will happen is that we should be able to find identical results between MICAS and the low scale Morito. When I say identical results, I am saying we have exactly the same critical densimetric Froude number for which the final angle is equal to 0. We'll find the exact same slope of the evolution of the final angle with this densimetric Froude number. And we will find the same constant angle when we have high densimetric Froude number. In that case, and only in that case, we will be able to conclude that the conservation of the densimetric Froude number ensures the similarity of the flow. And so we could be able to conclude that we have no scale effects if the densimetric Froude number is kept at the core exit from a scale to another. But there is low probability that it happen, maybe, who knows. But if we have some differences, because we have to anticipate that kind of results, if we have just one difference on one of this item, just on the critical or maybe on the flow, on the slope of the evolution of the angle, if we have just one difference on an item, what will happen next is that you have to study, do you have, how does the differences, evolve with the scale factor? Maybe it is something linear. Maybe you have an angle that is, okay, when you multiply by 2 the size, maybe the angle is multiplied by 2. Then you will be able to find, you will be able to find something to still transpose your result, because you will be able to find a relation between your phenomena and your scale factor. Then what you can also do is to study how does the differences you find from a scale to another, how does the differences evolve with other dimensionless number. So you can perform some experiments by changing the Reynolds number, the Euler number. You can try to find, okay, what are the force ratio that we thought were negligible, but in fact were not. And in that case, anyway, the first conclusion we will be able to draw is that the conservation of the densimetric Froude number only is not enough to ensure the similarity of the flow. So now, as a conclusion of this webinar, I can just say that keep in mind that all experiments on small scale mockup may lead to scale effects compared to a prototype. You have a lot of ways to avoid scale effects, or at least study them. You have some complex approach for everything that is transient or too fast flow phenomena. This is what happens a lot if you do some bibliography about the loss of Coulomb accident, for example, in PWR. You have different scaling techniques for integral effect tests. You can perform some calibration with scale 1 results. But then when you have to perform yourself a scale effect analysis, you have you have the dimensional analysis and scale series to find experimentally the scale effects you will have between a mockup and experiments, and then to be able to validate the simulation code you are using. So on this phenomena, to conclude this webinar, the ongoing study are about the scale series. We have some ongoing studies with the scale series using MICAS as a reference scale, and scale 1 to 1/2 and scale 1 to 4, the Morito mockup. Right now, we already could be able to show dependency of the jet angle with the dosimetric Froude number. So it shows that keeping at least the dosimetric, Froude number will be important in our study. Maybe it is not enough, but the first experimental results show that it is an important criterion to keep from a scale to another. Now we are just doing some phenomenological study on oversimplified mockup, the PINIA mockup, in order to have a better understanding of this phenomena before going on experimental campaign in the Morito mockup. The purpose of, sorry, as I said, it is still an ongoing study. The final conclusion of the scale effect on the phenomenon in French fast reactor, it should be known within a year when I will complete my PhD. So if you've been interested in this webinar, and I'm sure you've been interested in this webinar, you can keep my contact and look after my next publication. Then we will have the conclusion about the scale effects analysis we can perform in sodium fast reactor. Now I am showing you some references that may be interesting, especially if you have some really complex flow. I can tell you that these two references, the book Design Basic Accident Analysis Method for Light Water Nuclear Power Plants and the report for the Nuclear Energy Agency, they are showing an overview on all the scale effects and scaling techniques we can find in the nuclear field. Now I would like to thank everyone. First of all, thank the Gen 4 International Forum to make this possible, and thank all the listeners that were here. And if you have any question, we can discuss it now. Thank you very much.
Thank you, Benjamin. Thank you very much. I'm sure that we do find your presentation very interesting. While questions are coming in, let's take a quick look at the upcoming webinar presentations. In April, a presentation on the GIF IAEA joint webinar. It'll be a panel discussion on the role of nuclear energy in reducing CO2 emissions, which promises to be a very enlightening presentation, and all are welcome to join. In May, a development of anodized carbide dispersed advanced radiation resistant austenitic stainless steel, or otherwise known as ARES, for Generation 4 systems. And in June, a presentation on the nuclear waste management strategy for molten salt reactor systems. So if you have questions, go ahead and put those in the question pane. The only question that I see thus far is where's the link to the presentation? And there's a handout pane, either in your control panel, or if you're on a mobile device, along the top. Usually it's along the top of your mobile device, maybe along the margin of your device. There's a pane to download that PDF. If you still have difficulty, just shoot me an email and I will send you a copy. It will be uploaded to the GIF website along with the recording from today's presentation. Again, just give us a couple days to get the webmaster the information and get that upload completed.
It seems that the presentation was really clear, as there is still no question.
Yeah, I don't see any questions coming in. Congratulations again for your presentation in the competition in pitching your PhD. I think that the workforce has such promise in this next generation. I'm just thrilled to see the work that you will have in your future, Benjamin, and I wish you the best of luck. I think that you're going to make a huge impact, and you are just exactly what the nuclear industry needs.
Thank you very much. It means a lot for me. Thank you very much.
Yes, I echo the same, Benjamin. Thank you so much for your presentation. And I know you're doing your PhD and you took 1 hour, so congratulations. That's an exercise. And we wish you all the best For the audience, if you have any questions, it was very technical. You have the email address on one of the slides, so do not hesitate to contact Benjamin.
Thank you. Everyone have a great day.
Okay, thank you everyone.
Thank you.
Bye-bye.
Thank you very
Bye,
much.
Benjamin.
Have a good day. Goodbye.